Earth is really, really old. And in fact, it's almost 5 billion years old. And the very earliest Earth, that very beginning 1 billion years or so, we call the Hadean. Meteorites bombarding lava flows at the surface, an atmosphere that was poisonous to everything. It was Dante's Inferno. The Hadean, however, was a really important period in Earth's life because that's when we transitioned from this hell-like environment to one that has liquid water, oceans, is temperate climates, nice temperature, and of course, probably most important for us, it harbors life. There are very, very few vestiges of that ancient time available for us to study. Over the past 500 million years, of course, we know about the history of life and evolution by studying fossils. Fossils are buried in sediments that are built up on the seafloor. There are no sediments preserved from the Hadean. So we have to go to other places to look for the evidence of life. And probably the most important thing is to think about what life is made of. Carbon, of course, hydrogen and oxygen. That carbon has a very, very special signature in it because life processes enrich that carbon in a light isotope of carbon, carbon-12. And that's a signal that stays with that carbon even when the oxygen and hydrogen are lost. So the question is, where do you look if you want to find some residual record of this life carbon? And the answer came by serendipity. A graduate student at the University of California, Los Angeles, Elizabeth Bell, was looking at the mineral zircon. I don't think she was looking for life carbon, but she found a little bit of this life carbon in one of the most strange places you could probably imagine, and that's in a crystal of zircon. Zircon is a special mineral. It's made up of zirconium, silicon, and oxygen. And those elements make it extraordinarily tough. It's very hard, and it doesn't dissolve at Earth's surface. That means it survives. Zircon is a survivor. How were these zircons found? They went to Western Australia, collected a bunch of sediment, cut it, polished it, and then looked at it under microscopes, and eventually they would have taken it to a mass spectrometer. And what a mass spectrometer does is it separates atoms of the same element according to their mass. Well, that's where we get into isotopes again. And that's where we get the carbon-12 to 13 ratio. When she was able to make that measurement, it hit the bullseye as to what carbon-12-13 ratio should be in carbon from living matter. She knew that if she could find that carbon-12 signal in that graphite that could be dated at 4 billion years old, that she would have found the oldest evidence for living processes on Earth.